I make a short introduction. As I mentioned, my name is Murat. I'm co-founder and CEO of Magnimind Academy. First, I appreciate everyone for the class. You guys come Sunday morning and you take time and you like to learn. It's a great enthusiasm. That's what we like. Second is, I make a certain, I will just introduce myself a little bit. My name is Murat. I'm a Stanford scientist. I'm also an entrepreneur. I have a company called Smart Lens. We make contact lens for eye pressure measurement. So I also worked in data science last 20 years. I did a lot of biotech, bioengineering, bioinformatics research. And here, last several years, we've been working on optimizing data science, machine learning, education, and Magnimind. The Magnimind Academy, we've been trying to provide several free machine learning data science teachings. We have done a lot of meetups, boot camps, and we have a lot of workshops as well. We organize over 100 free programs and events. We appreciate if you guys can go make a review on several review channels, and our friends may share it where you may review, especially in Yelp, Google, and some other locations. If you can make a review, I would appreciate it. And it's been a lot of effort in our team to bring together such free events. I even say that those free events will be enough for several people to just start to work on the data science projects. And in fact, we have a lot of meetup that covers diverse topics in data science that many data scientists not even heard of it. So it may give a great broad understanding, as well as our programs, free programs may give a focused understanding of certain topics, including this one, Python class. We have time to time deep learning classes as well. So again, we appreciate if you give us feedback, and I will ask my friends to share those feedback channels. And for this class, I like to thank Dr. Geron to cover it up. So he's actually giving the fundamentals of machine learning. And this one is giving you a good understanding of how the machine learning algorithms work, what the machine learning is, and you get time to time some practice examples. So saying that, I want to introduce our mentorship bootcamp, which you may have heard in the beginning. And we are getting applications now and deadline in a few weeks, but I recommend everyone to just apply earlier because we start to make interviews. Hope we can interview with every applicant. So we generally prefer to accept people who complete this class, which you are trying to complete it, because this class is the real base and prerequisite for I should say content of this class is prerequisite for our bootcamp. So I will share the screen if I can. So our bootcamp, you guys see the screen, I believe. Let me see. So I have several components. Our goal with our bootcamp is whatever you learn in data science, you may be able to get a good understanding to apply in projects. So we work on the real projects, and we have several modules. In each module you have, I'll show you the modules, you have ML and NLP deep learning modules. And each module you're working with a mentor. So each module you have 3 mentors. So sorry, 1 mentor, and there will be 3 technical mentors. Then you work on projects that from companies or from Stanford we work with, and you get to have an understanding of how to work with the project. And then we also bring mentors from different companies around the Bay Area where we are. We are in Silicon Valley. And they give you understanding of how the ecosystem is, how the data scientists work. Just to say that are also some of our mentors also, technical mentors also from those companies. We give practice interviews, and we give career coaching and resume support. We follow up with our graduates after the bootcamp as well. And there is also a chance to do internship with companies who completes our program and who shows the good enthusiasm, and then who can understand, who can complete all the tasks. There's opportunity for internships in companies as well. So this is like a general overview of the bootcamp. So if you guys interested, I highly encourage to apply before the deadline, because we may not able to complete all interviews. We're trying, and we have also limited space. Again, we give priority to people who gone through our prerequisite program. That's why we got several applications, but we prefer to people from this bootcamp. So if you guys have any questions, you can just send us an email, and you can actually contact any of us. We can provide more detailed information. And I will let Dr. Jeran start his session. I hope you guys enjoyed. There's one more week. Hope you get a good grasp of data machine learning. Thanks.
Yeah, you can see the screen, right? Yeah, today's material was already added to the, yeah, thank you. Today's material was already added to the folders. So we are using the same material from last week. So module 3, because we couldn't finish the material last week, if you remember. So the way we're gonna proceed today is I'm just going to start with some lecture. And then we're going to continue working on the pre-processing file that, again, we started working on last week. So let's get started. So again, another reminder that most of the notes and code snippets that you might be seeing in this class are from this textbook, Introduction to Machine Learning with Python. So just to give the credit for the material that I have been using, the class notes and some code snippets from this book, Andreas Muller's book. And yeah, we started talking about pre-processing last week. And there are a couple of things that we do when we pre-process data. Actually, pre-processing will take most of the time or the effort we are going to put on a project when we deal with a data project. And again, most of the time, the real life project, right? So people are asking for, what is the real life project? Can I work on a real life project? Actually, what makes a project a real life project is this pre-processing step, because it's going to be really painful to turn data into a workable format so that we can implement a machine learning algorithm or some deep learning algorithm on the file. So to bring data into that format requires some work, and that is the pre-processing part. So there are a couple of main steps in the pre-processing. The first step, one of the steps, and then it's hard to put them in order, but I mean, we're gonna do our best. One of the first step is missing values. Yeah, we have a lot of data, and actually so much data, and I mean, if something is missing, why not just get rid of that data point, right? If anything is missing from the data, why not just get rid of that data point? Missing data means when you have this table where the rows are corresponding to the observations and columns are corresponding to the attributes, right? And if you see that for a row, one of the attributes is not properly recorded, or there is no value for that, then we say that that data is missing, right? So our first reaction for missing data is simply just remove that entire row, that observation from our data set, and sometimes remove the entire column from that data set. Because we have so many data points that removing some may not make any difference. That's how we can think, right? And that is normal. But the real life projects, right? Most of the time, the data sets that we're gonna have are gonna be imbalanced. Imbalance means if it's a categorical data set, like we are trying to classify something, like we want to see who has cancer and who hasn't. I mean, maybe let me give you a nicer example. Let's say we want to predict who's going to be churning and not churning, right? So it's a churn prediction problem. Or we want to predict who's going to be opening an email or not opening an email because we are sending some marketing email to customers, right? So for that, the data sets that we're going to be working on will be imbalanced, means only a few % of the customers will open an email, maybe 1%. So you are receiving emails from Magnimind. I hope you guys are opening the emails, but in general, when we receive some marketing emails, we're not gonna be opening them mostly, right? Or a few percentage of the people will have, say, cancer, or I mean, a few of the customers will stay in the same hotel in the next 1 month, right? So we're gonna have very imbalanced data sets. When we have imbalanced data sets, removing an observation, if that observation belongs to the minority class, right? Then we are simply losing an important part of the data set, right? So for that reason, when we deal with missing values, our first reaction is removing the data points, but we are gonna be careful about that. And sometimes missingness might be informative. For example, you are asking a question to customers, and you're not directly asking, but you are asking them to fill up a survey after you complete some service to them, right? And then some questions people may not be answering, and then you don't have data for those questions, right? In that case, if the question is privacy related, and if someone is not answering that question, so this missingness is informative, right? So you may simply infer that this person is, more protective in terms of privacy, protecting the privacy, right? So missingness might be informative too. Okay. So how do we get missing values? Let me remove myself from the screen. Okay. So as you see on the left side, this column has so many missing values. This is not a number, right? I mean, yeah, I would simply get rid of this column. So, I mean, it looks like this column is useless. Another way maybe we can have missing values is the entire row, in this case, has missing values. Again, there is not much I can do about this row. I can do things, but what's going to happen is this row and this row will look like similar to each other and may not be very useful. Again, there are ways we can try our best to make them useful, but again, we can maybe remove these data points. I don't even know, whether this data point belongs to a certain class, right? I don't even know that. So I can simply remove these data points. But there might be cases where the missing values are not that common, right? And like in this case, on the left-hand side, you see on the screen. And in this case, if you look at the first observation, only one attribute is missing. And I might want to keep this data point in my data set, right? So how can I keep this data point in my data set? When I run my machine learning algorithm on this data set, and I want to take advantage of these 3 attributes that I know the values for. So how can I take advantage of this row, right? So for that, I'm going to be using imputation. Means I will try my best to fill in those missing values with some reasonable values, right? What does that mean? Reasonable, what does that mean? Right? So there are ways we impute or fill in those missing values, and those ways we're going to be following, we might be following an algorithm for that, right? So let's see how we can make this imputation work. There are a couple of methods that we can do. The easiest one is just fill in the missing values with mean or median if the missing value is a continuous variable, right? Or we can simply fill in with the mode or the frequency if the missing value is a categorical variable. That is the easiest part. If you like, instead of using mean, median, or mode, what you can do is you can use a model to fill in the missing values. And I'm gonna try to show you examples on this. Okay, so let's look at the baseline model. Just 1 second, let me see if there are some questions.
Dr. Jeran, did you share the module 4? Are you going to share this?
This is module 3. I already shared this.
Okay, good.
Yeah, I didn't share anything for module 4 because we're not done with this one yet. Yeah, we can use different formats for missing values. NaN is one of them. I think Pandas is using NaN. You can use other notations for missing value too, and they mean different things. So we have to be careful. So for example, in your data set, you might have a question mark as a missing value. Question mark is a string, a character, right? Actually, it's not gonna be missing value if you, for example, could put question mark for a categorical variable. Your data set is gonna treat that question mark as some value, right? So it's one of the categories like student, faculty, staff, and question mark. There are 4 types of people in this university, right? So question mark is obviously missing value, but in this case, I mean, your code will not treat this as missing value. Then you need to look at your data carefully. You need to know the context a little bit to make a decision on whether something is missing value or not. Okay, so before we start with dealing with missing values, the baseline model that we're gonna compare the upcoming models with will be the model that we are going to do with by removing the missing value. So in this case, here, this line here actually is it's like a true-false vector, right? Boolean variable. What it does is it tells you which columns have any missing values. Even if a column has even 1 missing value, then it's gonna turn out to be true for that column. If a column doesn't have any missing values, then you're gonna have false for that column. So this non-underscore column, this one will have true, false, false, true, and a vector of true and false Boolean values, right? So the next thing is what I'm gonna do is, so this is my trained data set. I will keep all the columns that are that don't have any missing values. So this not non-columns. Non-columns will be true for any column with any missing value. Okay. So not non-column means all the columns without any missing values will remain in my data set, and then I'm gonna drop the columns with even 1 missing value. So in that case, my X drop columns will be only the columns without any missing values. If you look at the previous picture, so my I'm gonna be dropping this column, the whole thing. So my trained data set will have only 3 columns. Again, I'm working on my baseline model. So, sorry. The next thing is I'm just going to run my logistic regression model on this smaller data set. Smaller means one of the columns is dropped. And I am creating a pipeline, and we'll learn about pipelines today. What happens here is I create a pipeline, so I'm using make pipeline scikit-learn class for that. And I import this from pipeline library from scikit-learn. And there are 2 main ways of creating pipelines, which we're gonna learn. So what this pipeline does is it first scales my data set. Again, remember from last week, and I'm going to mention scaling in a minute again. So I take my data set and then I scale my data set using standard scaler. Standard scaler means I subtract the mean of each column from that column and then divide by the standard deviation of that column. And then after I scale my data set, the next thing is I am going to run my logistic regression, which again, we didn't learn, but it is a classification algorithm. Classification algorithm, we are using classification algorithms when our dependent variable or our target variable is a categorical variable, right? So I'm gonna be classifying my data points using logistic regression, okay? So that is my pipeline. And I'm gonna be running this pipeline in a cross-validation score. Again, remember cross-validation score, we are creating 10 models, and then I am taking the average of these 10 models, right? So this mean is the average of 10 scores, each score corresponding to one model. And my baseline model, after dropping the columns which have missing values, this baseline model, its accuracy is 0.76. So if I'm going to be using imputation, means if I'm going to be filling in missing values, I expect that at least I should be doing, in terms of success rate or accuracy, I should be doing as much as this score here, right? Because this is my baseline model, score for my baseline model. Okay. Let me see some questions. Just 1 second, let me check the questions. Yeah, what is this tilde in tilde non-columns means not non-columns. Non-columns is true, false. Tilde non_columns is, it changes true to false, false to true. It is not. So not true is false, not false is true, right? All right. So I said the simplest way to fill in missing values is using mean, median, or frequency. To do that, we are going to be using pre-processing library of scikit-learn. And to fill in missing values with the mean, it says imputer, but this is the old version. It's actually simple imputer. So it does the same thing, just the name is changed from imputer to simple imputer. So please just be careful about this. It's not imputer, simple imputer. And again, I'm gonna be instantiating my simple imputer with strategy mean. So strategy mean means I will be filling in these missing values with the mean of that column, mean of all the non-missing values in that column. Again, imputer, a simple imputer is a transformer. Scikit-learn, for transformers, we need to use fit. So imputer, simple imputer, strategy equals mean is my imputer, and I need to fit my imputer on my trained data set. So the moment you fit your imputer on your trained data set, this imp object now has the mean of the columns. And then when you transform your trained data set, your imp object will replace all missing values with the mean. As you look at on the right-hand side, I am plotting the last 30 data points. If you look at the right-hand side, as you see, the missing value here is replaced with 1.462. The missing value here is again replaced with 1.462 because the mean is the same for this column. The mean of this column is 1.462. The next column on the left, the mean value is 4.116. That is the mean of the non-missing values on this column or in this column. All right, this is mean and median. If you plot your data points, right? If you plot your data points, now the square ones are the imputed data and the circle ones are the real data. So real data means data points that you already have the values for. Square ones are plotting these values, which you actually artificially, right, filled in, right? So as you see, the green ones, right? This green belongs to a different class, orange belongs to a different class, and blue belongs to, data points belong to a different class. And blue ones, as you see, don't have any, in this attribute doesn't have any missing values, the blue ones. But the green ones have missing values, right? Green ones have missing values. And as you see, the green, I have 3 different categories in my data set. A certain category, let's say staff, they don't have any missing values, but students are the green ones. Students have some missing values. And in this, on the screen, I am plotting 2 of the attributes of my data points, x1 and x2, 2 attributes. This is 2-dimensional plot, right? So as you see, for let's say attribute x1, all these square ones are corresponding to the same value. And again, for x2, all these square ones are corresponding to the same value, because again, for x1, I have all 1.462 for all missing values, and for x2, I have only 4.116 for all missing values. So that's why I see this constant values, right? Or constant values here, right? For x1 is fixed here, and then x2 is fixed in here. So this mean missing values, mean strategy doesn't look so good on the data set. I mean, it's not doing much on my data set, because I would like to classify my data points nicely. Like here, this is blue, and then I will have an orange, and then I will have a green. But it looks like classification will be difficult for me. At least linearly, it's gonna be almost impossible for me. Okay, so I'm asking myself if I can do better than this. So before going into the next one, what I do is, as you see, I'm using my simple imputer. Again, I am importing simple imputer from impute library. And my pipeline, remember, my pipeline was beginning with standard scalar. In the previous case, this is my baseline model. So my pipeline here begins with simple imputer. Then standard scalar comes next. Why? Because my pipeline tells me that first I'm gonna be filling in missing values. So this step here, I already did manually here, right? I already did manually here. Manually, I just removed the columns with missing values. But here, I'm not removing any columns, but I'm filling in missing values with the mean of that column, okay? After I do, by the way, pipeline will work in order of the estimators, transformers and estimator. A pipeline will have might have multiple transformers, and if it has, it'll have only one estimator. In this case, my estimator is logistic regression. And I have 2 transformers, simple imputer and standard scalar. So when I run my cross-validation score, this is my pipe object. I'm first going to impute my data set with simple imputer. In this case, I'm going to be using mean. And by the way, when I call my simple imputer, by default, it is taking the strategy as mean by default. And then I'm going to be standardizing my data set. And then I'm fitting my standardized data set with logistic regression on my trained data set. And next, I am going to be calculating the score for that model. And I will repeat this 10 times. You already know what cross-validation score means. And then taking the mean of the 10 scores, my mean score is 0.729. As you see, I used simple imputer. My score is actually less than my baseline model. So in other words, I'm doing better if I simply remove that column with missing values instead of using simple imputer. Okay. Then I ask myself if I can do better than this. Maybe instead of simple imputer, I can use some other technique, right? Okay, so just one second, let me check the questions. Yeah, all the missing values in the same column, if we are using mean or median as the strategy, will be filled with the same value, right? Yeah, so, okay. If you have large, really large data sets, right? I mean, and then the percentage of your missing values to the size of your, the ratio of your missing values to the size of your data set is not very high. And then these are all very subjective. I say very high, right? Or very large, because depending on the context, right? Then you might be using mean or median as a strategy. Simply use mean or median or simply imputed as a strategy, which may not hurt your performance, your model's performance. If you have a smaller data set, then I would use a predictive approach, which I'll describe in a minute, to fill in missing values. Yeah, I already uploaded the notebook from last week. You can download the same. I replaced the notebook with, so I already replaced that notebook. So you can use whatever is available in the link. So that is the one that was updated. Okay. Yeah, in this case, yeah, all the missing values in the same column, if you are using simple imputed, will be the same. So regarding missing values, so we are going to be dealing with missing values on our trained data set, and we are going to. So let me explain this a little bit. Let's say you have some trained data set as you have here, and then you ran your simple imputer. Remember the simple imputer, that what simple imputer does? Simple imputer simply finds at this stage right here, when you fit on your trained data set, simple imputer is going to find the mean of your column, right? The mean of the column. So this imputer will have your mean of the column. So in your test data set, when you receive test data set means a new data point, right? A new data point that is not included in training the model. When you receive a new data point, and let's say that data point has some missing values. So you are going to still use imputation on this new data point, but you will use the imp object that you already fit on your trained data set. In other words, you are going to be filling in test data set, the missing values in your test data set, with the values that you already recovered from your trained data set. And that is the realistic approach, right? So when you receive a new data point, I mean, you already have some training data, some historical data set. From the historical data set, you already have which values you should put for missing values, right? When you receive a new data point, you are going to simply replace missing values in the new data point with what you have already found from your trained data set. So cutoff will be difficult to answer that question. There was one question on what is the cutoff for data points. It's difficult. Again, depends on the context. And if I'm dealing with highly imbalanced data set, I will do everything, try everything to do my best to find the best approach to fill in the missing values. So I can try simple imputer and model-based imputation, and then see which one is working better. All right, so as you see, simple imputer looks like doing worse than our baseline model. Next, let's use some modeling approach. What is modeling approach? In this case, for my model, I'll be using KNN imputation. We already know what KNN is, right? K nearest neighbor. Okay, so what is K nearest? This is the code from scratch, which actually does KNN imputation. But the idea is the following. Let me talk about the idea. And by the way, the reason why we were late today for 7-8 minutes was I was trying to connect with my iPad. Somehow, I was using my iPad for these classes. Somehow I cannot use my iPad for Zoom. I don't know why. I cannot share the screen. It doesn't show me share screen. So normally I was writing on my iPad and it would be much easier for me to explain this. Anyways, so let's talk about KNN imputation. So what KNN does is the following, all right? So if I want to fill in this missing value here, so I want to fill in this missing value. Okay, you can see the arrow, right? You can see the arrow, this cursor. I want to fill in this missing value here. So what I'm gonna do is, I'm gonna find for this guy, for this observation, I'm gonna find the closest neighbors. K closest neighbors. It can be 1 or 2 or 5. Okay, K close. I'm gonna find the closest neighbor with respect to the non-missing values of this observation. What are the non-missing values of this observation? 5.1, 3 point. So I will be using these 2 columns to find the closest neighbor to this guy. Okay, to this guy. When I find the closest neighbor to this guy, if it's only one neighbor, if I'm using K equals 1 nearest neighbor, then I will simply replace these missing values with the values of that neighbor. Again, when you find the nearest neighbor, you're gonna be finding the neighbors from those who do not have missing values for these data points. For example, this is a candidate for nearest neighbor. This is another candidate for nearest neighbor, right? So if this or this or this, whichever is the closest neighbor to this guy, and when I find closest neighbor, of course, with respect to these 2 values, because these are the ones which are not missing, so I can only find closest neighbors with respect to these 2 data points, right? These 2 attributes, these 2 attributes. Let's say this guy, 5.5, 4.2, 6.3, 2.3, 4.4, and 1.3. Let's say this observation is the closest to this observation in terms of these first 2 columns. So in that case, what I'm gonna do is, I will simply replace these 2 missing values with 4.4 and 1.3. So this is KNN nearest neighbor. If you are using 1 nearest neighbor, you will find the best neighbor, 1 best neighbor. If you are using 3, then what you're gonna do is you're gonna find 3 neighbors, and you're gonna take the average of the values that are corresponding to the missing values in your neighbors. So simply you are using your neighbors' values, you know, to fill in your own missing values. If I have missing value, I will find some neighbors who do not missing values for those attributes, and then I will simply replace my missing values with my neighbors' values. That is KNN. See some questions. If you have outliers, I would recommend median rather than mean. Yes, yes, Adi. All right, let's continue. This is KNN, and after I fill in again, scikit-learn has a class for KNN imputation, or you can simply write your own function, which is here for imputation. So this is the function that actually finds the closest neighbors and then fills in. So this is KNN imputation. This one. So now we plot the data set, the same data points. Again, these squares are the missing values but we replace them with some neighbors values, right? With some neighbors values. So now you see, I have a better looking data set, right? Looks like I have this class more centered here, and I have this class more centered here. And actually, when I run my logistic regression, again, logistic regression is a linear classifier. So it is easier for me to actually classify these data points, right? So I can draw a line here. This part is orange and this part is green, right? So look at the score. Score is improved, right? Score is improved from 0.72, in this case, 0.849. So actually, the way our data looks like also tells us that the model will work better on this data set, right? Okay, now, is there other ways of filling in missing values? Yes, there are other ways of missing values. Similar to what we did with KNN, we can use other models to fill in missing values. Again, we're gonna do similar thing. So in this case, I'm using random forest regressor. You can use linear regression, or decision tree. You can use any other model to fill in missing values. And how is this happening? How is this happening? Let's go back to our picture one more time. Okay, now, this time, here is what I'm gonna do. Okay, this time, here is what I'm gonna do. I'm going to focus on this column, all right? I'm gonna focus on this column, and I'm focusing on this column to fill in missing values in this column. What I'm gonna do is, all the missing values in this column, I will separate them. Okay, those data points, I will separate them. I will put them aside, and I will treat them as my test data points. Right? Remember, what is the test data point? Test data points are the ones that we are predicting the target values for, right? So I will treat these data points as test data points. So I will put them aside. All the values in this column that are not missing, like 1.5, 1.8, I will treat them as my target value. Remember what target value is? It is the label value, right? So if you are predicting income of individuals, and if you know a person's income, so that person will be your training data point, and his income will be a label value because you know his income, right? So this is the supervised model. So all the data points that I know the value of will be my target value label. So this column will be my target variable. This column will be my target variable. The values that I know in this column will be my training data points. The values that I don't know the values of will be my test data points. All right. What happened to the other three columns? The other three columns will be my attribute set. Remember, the first class we said we have an attribute set and a target set, right? A target column and an attribute set. So I'll be using this as a target variable and the other three as the attribute. And remember, I already divided my data set into two pieces. One is test data set, the other one is train. Train data set consists of data points with non-missing values. Test data set consists of data points with missing values. So using my training data points, I will train a model. In this case, I'm using random forest classifier. I'll train a model on these three, using these three columns as my attribute set, and this fourth column as my label. Okay, I'll train my model, and then I will predict the values for these missing values. Okay, this is the way we are using model-based imputation. Again, I'm focusing on this column here. This column will be my target variable, and then all the data points with missing values in my target variable will be my test data points. All the values with all the data points with observations with non-missing values in this target column will be my training data point. I'll be using these three attributes, okay, as my attribute set, and this column of my focus as my target variable. I'll train a model on my training data points, which are the ones with non-missing values on my target column, and then I will predict for the missing values in my test data set. I hope it was not very confusing, right? It's not confusing. Actually, we are simply doing a trick here, right? So we are simply estimating values for our missing values, right? And look at the score now. Sorry, 0.855. See, it's even better than the previous one, KNN. So if you look at how random forest imputation looks like, it looks much better than KNN. So this is mean, this is KNN, this is random forest imputation. Okay. All right, so let me just take a moment to see if there are any questions. This is the link to the material. If missing value account for the majority in a column, what should we do? Again, depends on the context. you can still try to fill in those missing values to see if you can improve the predictive power of your model. Okay, so I will always try my best to keep data points in my model. Again, if I don't have I don't have a large data set, or if my data set is heavily imbalanced, I will do my best to keep my data points in the model. Okay. Are there cases? Yeah, that's what we are doing, right? So this that's what we are doing. So I'm reading the question: are there cases where we should build one model for the good rows with no missing data? So that's what we are doing. So we are putting the column with missing values aside. That is the target variable, and we are using the other columns to make prediction for the missing values. Okay. All right. For binary classification, I mean, binary or multi-category classification, right? So that's the different story. So that will come after you have imputation or data set. So right now we are pre-processing data set. Once we pre-process our data set, then we are going to use classification or regression on our data set, right? So at this stage, I am pre-processing my data set. Okay, let's continue. Scaling. So we already mentioned scaling, so I will be very brief on this one. So we talked about missing values. Now I'm talking about scaling. Scaling will be relevant when your data points, when your columns are taking values from really different ranges. For example, one column can be taking values between 1 and 5. Another column, attribute, might be taking values between, in terms of thousands, right? So in that case, there are certain algorithms that are specifically sensitive to having really different ranges of values, right? Very sensitive. So for that case, we might need scaling, right? Okay, so let's look at, remember this box plot from last week, right? We created box plot for our Boston housing data set. So this is a different Seattle housing data set, but the same thing applies. So this column, square foot of the lot, right? It is taking values from hundreds to, 10,000s, right? And look at this floors, it's taking values from 1 to maybe 3, right? Right. So again, look at this bathrooms, it's taking values from, hopefully not 0, from 1 to maybe 5 or 6, right? So bedrooms taking values from 1 to, I don't know, 6, 7. So you have 10,000s here, you have 1 to 6 here. So very different range of values, right? So this begs for scaling actually, right? So let's see, what is the impact of scaling on certain algorithms? Certain algorithms do not really care about scaling. Decision trees don't care about scaling. Decision trees, very nice thing about decision trees, they don't care about scaling. So let's look at this data set. I have only 2 attributes, x1 and x2, and I have my blue and red data points. There are 2 classes. So as you see, look at the x-axis, my data points are taking values from 8,000 to 12,000. And look at the perpendicular axis, y-axis, my data points are taking values from, let's say, -0.6 to 6, right? Clearly, it's a very different range. This is without scaling. When you scale these data points, now as you see, x-axis also takes values from, say, -1.5 to, say, 2.5. So both x1 and x2, or x1 and x2, or horizontal and vertical axis, they both are having values from the same range, right? Okay, this is width scale. Okay. Look at the impact of scaling on KNN. Again, remember, KNN, K nearest neighbor, is an algorithm that is very sensitive to scaling because it is based on distance metric, right? Distance metric. So when you are using data without scaling for KNN, most likely your algorithm will give you really bad results. Like here, right? Look at the blue region is blue data points, red region is for red data points. So this X here, the axis here, will be dominating the algorithm. Now look at the right-hand side. Because your data points are from the same scale, now the border separating red from blue is doing its job, right? So your KNN is working with scaling. It's not working without scaling. Okay, then what type of scalars available for us? The most common scalar that we are using is standard scalar. So this is your not scaled data set. This is your not scaled data set. There are two things that you should consider here. First, your data points are showing a certain dispersion, right? So variance along a certain, your data points are varying on X and Y axis, but mostly on Y axis, right? So the variance is higher on this axis here, right? Second, your data points are away from the origin. They are not centered. So centering the data points might be helpful for certain algorithms. Okay. So let's say that much now. All right. So my goal is I would like to scale my data set. And another thing you observed, your data points are taking values on x-axis, taking values between, say, 10 and 15. And on y-axis, taking values from 1 to 10. Not very different, but if you look at here, most of your data points are taking values. You don't have any data points less than 10 or greater than 15, right? So the variance is very small in your data. For your data points, the variance is really small on x-axis. So when you do standard scalar, what you're going to do is you are going to find the mean of your data points, mean on x-axis and on y-axis. You're going to find two means, x-axis and y-axis. You're going to find mean of each column. And then what you're going to do is you're going to subtract mean from your data points. Subtracting mean from the data points means you are shifting your data points to the center. So that's what's happened. Okay. If you just did this, if you just subtracted mean from your data points, you would still have the same shape, but centered here. So it would still have the same shape, but centered. But we did one more thing. What is that? After we subtracted mean from our data points, we divided by the standard deviation of our data points. Why? By dividing standard deviation, what we are doing is we are actually controlling the variance of our data points. In other words, our data points now are varying similarly on both axes, not only centered, but as you see now, my data is spreading similarly on both x and y axis. So that is standard scalar. So this data set has 0 mean and standard deviation of 1. Just keep in mind, standard deviation of 1 doesn't mean that your data points cannot take value more than 1. So your data points can take 2 standard deviations away from your center, okay, or negative 2 standard deviations away from your center. But most of your data points will be centered within this circle. Maybe 85% of your data points will be centered in this circle. What is the circle? It's the circle with radius of 1. Okay, that is standard scale. All right, let me see if any questions. Successful completion of this class means you just come to class, okay? And then I hope you guys are looking at the homework assignments. I posted an assignment for this Saturday. I hope you guys did your homework. I'm going to post another homework for this session too. Okay. So this is standard scalar. Another very common scalar is min-max scalar. So what min-max scalar does is, look at min-max scalar here. Look at your data points. What it does is you are going to subtract the minimum from your data points and divide it by the maximum. You're going to subtract the minimum and divide by maximum. Think about it. What happens if you do this? If you subtract your minimum from your data points, the transformed data point, the minimum will be 0. And if you divide by maximum, the maximum value of your data point will be 1. So basically what you're doing is you are squeezing in your data points between 0 and 1. You see, my data points are between 0 and 1. This is min-max scale. I don't have any negative data points now. All right. So these are the two very common ones. For some algorithms or for some cases, we are going to be using min-max scalar. We're not going to be using standard scalar. Okay, just please just pay attention to this point. Look at standard scalar. When you standard scalar, your data points will have negative values. Okay. For example, there are certain transformations that you can do on your data set only if your data points are positive. If you're going to apply those transformations, which I'm hoping to talk about them later, if you apply those transformations on your data points, then you should have all non-zero data points or non-negative data points. In that case, applying standard scalar is not going to work because you will have negative values. Second, you might have data points with lots of zeros. So what does that mean? What does that mean? Lots of zeros. You might have data points with lots of zeros. For example, if you are working on text data set, right? So, and then very primitive project, which you are giving one to, we are creating a vector, and that vector will have 1 for the words that you have in your document and 0 for the words that you don't have in your document. So think of all the words in English, and I give you a document. For this document, you create a vector. In this vector, each member of the vector is corresponding to a word in English. So how many words in English? Let's say 2,000. Let's say, okay, 2,000. So you have a 2,000 size of vector, and then you will only have 1 in that vector. You will only have a vector member equals 1 if you have the corresponding word in your document, and the rest will be 0. So in this case, your data set will have mostly zeros. So if you apply standard scalar or min-max scalar on this data set, okay, I'm sorry, standard scalar on this data set, what's going to happen is all these 0 values will turn into non-zero. Right? So why is this important? You might choose to store your data points. If you have so many zeros, you might only choose to store non-zero elements of data points to save from memory. Okay, so for these kind of data sets which have lots of zeros, we choose not to use standard scalar, because standard scalar will turn all 0 elements in your data set into non-zero, because with standard scalar you are subtracting the mean. If the mean is not 0, which most likely it's not going to be 0, when you subtract mean from your data points, automatically your data point will turn into a non-zero element. Okay, let me just move to the, that's what I was talking about, sparse data sets. Let's check if no questions. Okay. Yeah, standard scalar is similar to conversion of standard normal distribution with mean 0. And yeah, when you apply standard scalar, you're actually turning your data set into having your data points will have standard normal distribution with mean 0 and standard deviation 1. I'm talking about continuous attributes, okay? Should we scale data with a center in a region away from 0 / for example, with a center far enough from 0? Yeah, okay, so that's a good point. So let me sometimes in your data set, for example, think of this, okay, think of this data set. You have one data point right here. It's an outlier, okay? It's an outlier. It can be even further, okay? I don't know, the cursor is outside the screen. So in that case, if you take the mean of this data set, the mean will be carried away by this outlier, right? And you don't want this to happen because most of your data points are actually clustered here and you have a few outliers, right? So in that case, as part of the pre-processing, you might, first of all, consider eliminating some of the outliers. You can put a cap. If any data point is above or below, say, 85% range, I will simply, or 90% range, I will simply eliminate them. So you can put a cap and then drop some of the outliers. That's one thing. Second thing is to address that issue. Actually, we have this robust scalar. So with robust scalar, what we do is instead of using the mean of the value, mean value of the data points, with robust scalar, we are using 25 and 75 percentile values of our data sets. So we are subtracting not just mean, that's why it is robust. We are using 25 and 75 percentile values of our data points so that we are minimizing the effect of the outlier on, let's say, 75% of the data points, right? So there are ways you can actually limit the impact of outliers when you are implementing standard scalar on your data set. Okay, let's look at this standard scalar example. Again, I split my data set into train and test. And as I said before, I prefer implementing my scaling after I split my data set because I am going to use my scalar that I found on my train data set. I'm going to use the same scalar on my test data set. That's why I first split my data set, okay, as here, train and test. Next, and this is one of the mistakes that people do frequently, we do frequently. So after I split my data set into train and test, I instantiate my scalar. And then this is my scalar object. And then I fit my scalar on my train data set. So the moment you fit, what happens is now this scalar has an attribute, which is scalar has attribute, which is holding the mean and standard deviation of all the columns in my train data set. Okay, of all the continuous columns in my or numeric columns in my train data set. All right. Now, after I fit my scalar, next thing is I'm going to use my scalar object to transform my train data set. So now my train data set is scaled. So basically, I took my data set, divided into two pieces, train and test, and then this is my scaled train data set. All right. Next, I'm using ridge regression, which we didn't learn about. So this is one regression algorithm. So basically, it's an estimator. We know how to use estimator from our previous class. I fit my estimator on my scaled train data set. By the way, I'm not scaling my target variable. In general, I don't scale my target variable. Okay. And I trained this model on scaled train data set. Okay. I train my model on scaled train data set. Next, I want to test my model. I can test my model on my test data set, right? So what I'm going to do is I'm going to take the same scalar object that was fit on my train data set. Remember, the scalar has info about mean and standard deviation of each column of the trained data set. So I'll use the same scalar and transform my test data set. So basically what I'm doing here is I am subtracting mean and standard deviations that I found on my trained data set. I'm subtracting them from my test data set in this case. So this is my scaled test data set. And next, I'm finding the score for my estimator object, which is ridge in this case, on my scaled test data set. All right, I hope this point was clear, which I will talk more about it, okay, in a minute. Let me check questions. Okay, guys, I'm back. So I see some questions about why train, not test data sets. So let me clarify it again with this slide, okay? And then we're gonna do, I remember like we didn't do step 5 and 6 last time. Actually, we have a lot to cover. I don't think we'll be able to finish today too, but I will spend some time on 5 and 6 just for scaling part. I think we didn't do 5 and 6 last time. If we did, then I can simply move on to the next topic. So, okay, let's look at this on the screen. Yeah, I'll try to explain this one. So let's look at this one, okay. On the left-hand side, you see the original data set. Again, blues are training, reds are test data sets, okay? These are the test data points. So just keep this relative location of data points with respect to each other. I have only 2 features, very simple. So what's happening here on the middle one? I am scaling, I'm fitting and transform my trained data sets. Okay, I'm fitting and transform my trained data set. When you say scikit-learn fit underscore transform means you first fit your scalar and then transform your trained data set. When you fit, as you remember now, this scalar, this object has all the mean and standard deviation, right? Mean and standard deviation of the blue data points, the trained data points, because you are fitting your scalar on your trained data set. Next, using the same scalar, you are transforming your test data set. Using the same scalar, you are transforming your test data set. And then you plot your data points, all right? Look at the features. At first, they were changing from, feature 0 was changing from -10 to 15, and the -15 to 10. Now they both are changing from -2 to 1, all right? So, but as you see, the relative positions of test and trained data points did not change. Look at this data point here. It's still at the same relative location with respect to these 2 and with respect to others too. So the reason why it didn't change is because I am using the same scalar that was fit on my trained data set. So when I fit and transform my trained data points, I get these blue ones, okay? When I transform my test data sets, these red ones, I am using the information I got from my blue ones. So that's how the relative location of my red ones with respect to blue did not change, right? Because I'm using the information from blue, that information coming from blue will keep my red data points in that respective locations, right? Now let's look at this one on the right-hand side. Again, I did my scalar, fit and transform on my trained data set. Now I got the same blue points that I got here. But I did something different here for my test data set. My test data set, I fit and transform my test data set. So what I did is now, I didn't use the scalar from my trained data set. I use a new scalar, which is fit on my test data. This new scalar actually now has the mean and standard deviation of only my test data points. When I subtract mean and divide by standard deviation, I'm using my test data points information. So I lost the connection between red and blue now. That's why, look at the relative locations of red with respect to blue, it's gone. So this is improperly scaled data set. Do not fit your scalar twice. Fit your scalar only once on your trained data set, and use the same scalar to transform your test data set as it is here. Okay, that's an important point. Actually, again, in this class, we're going to learn about pipelines. Pipelines will make this very easy for us. We don't have to really keep track of this, but we know what is happening behind the curtain, that we are using scalar only once, fit only our trained data set, and use it to transform our test data set. Okay. Second, if you try this, which is the correct version, right? Remember, standard the standard scalar, right? Standard scalar creates a scaled version of your data set with mean 0 and standard deviation 1. Now, if you look at the mean of your scaled test data set, I'm talking about this case in the middle, which is the right one. If you look at the mean of your scaled test data set, it may not be 0. It may be close to 0, but may not be 0. And this is normal because you are using the scalar coming from the trained data set. The scalar is using the mean of your trained data set. You're subtracting the mean of your trained data set from the test data set. That's why the transformed and scaled test data set may not have exactly 0 mean, but it is fine. It's going to be very close to 0, but may not be exactly 0. Okay, don't be surprised if you see that. Okay. So scikit-learn has estimators, right? We fit estimators, and then we predict with estimators, like for classification, regression, or clustering. Hopefully, we're going to learn clustering, regression, and classification. And we learned some classification, K&N classification. We use predict, right, to predict the class of a new data point. Right? The pre-processing libraries have transform method. Okay, so this is transform. Instead of predict, we are using transform. Don't mix these two. Okay, transform is used for transformers. Right? Predict are used for estimators. Okay. All right. So let's look at this. As I said, some algorithms are very sensitive to scaling and some not. Look at this ridge regression. It's a regression type of a regression. So this is the score without scaling, and this is the score after scaling, trained data set and scaled data. As you see, the score did not change. Normally, ridge regression is also sensitive to scaling, but it depends. Here, nothing happened. It's not that sensitive. It is sensitive, but not that sensitive. Look at k-neighbors regressor. Again, this is also a regressor, but we are using k-neighbors. Okay, remember k-neighbors, K and N is using distance as a metric. When you say distance, scaling is a must. Look at the score difference without scaling, with scaling. It makes a big difference. So you need to scale your data set before you use. I would scale my data sets mostly. Mostly. All right. Please pay attention to this point. Then I'll go to Jupyter Lab. Okay. I already mentioned this mistake that we are doing. So let's see how sophisticated a mistake we can do and think that we are doing really good. Okay. So let's look at this. This example here, example is a little bit different. I'm not using scaling. This is an exaggerated example. In this example, what we are doing is, as you see, our data set has 10,000 attributes. That means 10,000 columns. Okay, only 100 data points and 10,000 columns. This is really excessive, right? So what you can do is most likely, most of these columns are correlated with each other, which will create collinearity. So we might simply reduce the dimension of this data set. To reduce the dimension, there are different types of things you can do. This is also part of the pre-processing. Eliminating some of the features or feature selection. Feature selection is also part of the pre-processing. Some of the features in your data set may not be very relevant. You don't need them there. Or some of the features may be highly correlated with each other. One of them might be enough, okay? So here we are using the most useful 5% of the 10,000 features, okay? Just know this much at this point. As you see, from 10,000, we reduced our data set to 500 attributes. So out of 10,000, we eliminated 95%, and we only focused on the very important 5% of the columns that the top 5% of the columns. Okay. So how do you find this top 5%? What we do is we look at how each of these columns is related to the target variable. And then there is a metric that we can use how they are related. And then we are then sorting out all the columns with respect to that metric, and then just take the top 5%. That's what's happening here. That metric is, in this case, F regression, F score. Okay, so this is the transformer. This is the transformer. Here we instantiate the transformer. Here we fit the transformer on our data set, which is this one. And then here we transform our data set. Okay, now I have this transformed data set. It is not scaled. Scaling is different. Here, my transformed data set is data set with reduced number of features. Okay, next. I take my transformed data set. I use my ridge regression, and then I simply run cross-validation score. You know what cross-validation score is. You know why I'm using NumPy mean function, because cross-validation score is returning multiple scores. I'm taking the mean, and wow, look at the score, 0.90. 0.90, that is the score, okay? All right, so that means my model is really working perfectly, almost perfect, right? So next, what I do is I take my ridge regression, okay? I take my ridge regression because here I check how my model is doing with my cross-validation score. It says very good. Okay, remember what cross-validation score was doing? It was taking your data sets here. It is taking your data set and then dividing it into folds, keeps one fold aside, uses n-1 folds for your train set. And then after training the model on this n-1 fold, it calculates or computes the score on this single fold. All right. So your validation and your train data set are part of this X selected, your validation and train. And the score is coming from your validation data set. So I validated my model, and my model is working good. By the way, I should resume recording. I forgot about it. And sorry about that. I forgot the recording. Okay, this point is important. Next, I'm happy that the model is working. So I take my model and fit one more time on my entire data set. Remember, that is the next step, right? So if you cross-validation is good, then you are almost confident that you should use this model. So you take this algorithm, you take this algorithm and fit on your entire data set. So this is my trained model, okay? And then I take my test data sets and then I transform my test data set using the same select, which I already fit on my trained data set. So far, nothing looks really wrong, right? I'm simply doing what I told you before. I am using transformation. I'm fitting the transformation only on trained data set, right? I'm fitting my transformation only on my trained data set, and I'm using the same transformation on my test data set. But the score is really awful. What happened here, right? What happened? Why my score went down from 0.90 to negative? Negative means I'm doing worse than random guessing here, right? That's what it means. Why is it? Why is this big difference? Right? So let me just pause here. I'll continue. It seems like using. Okay, I'll try. So what if your test data is outside the limits of your, what if your test data is outside the limits of your trained data set? Means if your test data is totally different than your trained data sets, I mean, totally different means, the data points might be, like your test data point might be an outlier, right? Then your prediction will be poor for that data point. Yeah, then it will be, your prediction will be poor, right? Because it's an outlier in that case. Okay. So questions coming from QA and chat. So then interestingly, I don't see the new questions. Okay, sorry. Okay, so let's answer this. Oh, let's answer this question. What happened here, right? The thing is, what happened is we are leaking information. They are leaking information from validation data set into our training data set. Remember, we had two, when we are using cross-validation, we have train and validation, right? So this is what's happening here. Okay, what's happening here is exactly here. So what we did is we transformed the whole data set, and then we are splitting that transformed data set into train and test when we are doing validation. Here, I'm doing validation. Okay. The correct way is I first split into my train and validation. I transform my train. I fit and transform my train, and then I transform my test using the same fit transformation I used for my train data set. That is the correct way. All right. Inside, this is happening inside cross-validation, guys. This is happening inside the cross-validation. Okay. This is the correct way. Now, I understand that this looks like a lot of lines of code, like maybe confusing. So then we are going to take care of this, okay, without really getting into this much of detail. So here, how we can take care of it. First of all, instead of manually fitting my scalar on my train, and then be very careful about using the same scalar to transform my test data set. Remember, we went through this. Remember, we went through this code, right? Here, I'm manually fitting and transforming my train and test data set. I can do this using my pipeline, which we mentioned earlier, right? So I'm using make pipeline. Inside the pipeline, I have two things. One, a transformer, another estimator. The transformer is standard scalar, the estimator is ridge. Now, I take this pipe. Now, pipe is, you can give any name, my pipe, pipe 1, pipe 2. I take this pipe and fit on my train data set. When I fit on my train data set, the standard scalar is fit on my train data set. And scalar object is holding information from the train data set. Then I can use the same pipe to compute the score on my test data set. When you say pipe.score, this test data set will be transformed using the standard scalar that is holding information coming from trained data set. And then the prediction is happening coming from ridge regression. And then calculating the score using target variable. So all these are happening inside the pipeline. You not doing anything really. I mean, all these steps here are actually happening inside the pipeline. Okay, that's the first thing that pipeline will help us do. Okay. Now, you can put inside the pipeline many transformers, and you can have one classifier. You can change classifier to inside the pipeline. You can have one classifier, but you can replace the classifier. Okay. So what happens is when you have two transformers and one classifier inside the pipeline, and then when you take this pipe and then fit on your train data set, X, and this is your target variable. So what pipe will do is it's going to take your X, which is your attribute, set of attributes. First, it's going to fit and then transform, fit and then transform using transformer 1. Y is not changing. And then it's going to fit and transform the already transformed data set that is transformed using T1. Now we're going to do the second transformation on T1. T1 is a transformation of X. And then T2 is a transformed version of T1. And then finally, we are going to, finally, you're going to fit this twice transformed data sets on your classifier. X2 is the twice transformed data set. All right. So let's come back to our cross-validation. Remember, cross-validation, this was bad. What we were doing here was inside the cross-validation, we were doing the transformation before split, right, inside. So this one was good. This is manually taking care of that. So we are first splitting and then transforming. So you don't have to do this manually. What you can do is you can create a pipeline. What is this pipeline? This is the transformer select. Remember, select is selecting the 5% best features. And this is your estimator. So this is my pipeline. So I call my cross-val score class. And then I just use pipe here. That's all. So this line here, this guy right here, this is actually doing this entire thing. That's why I take the mean of this, because this one single line is actually returning these scores to me, right? So you can do the same thing wrongfully here. As you see, you first fit the entire data set and you transform the entire data set, and then you put this transformed data set into the cross-validation score. This is wrong. And a lot of people are doing this mistake. Don't make this mistake, okay? So for that, I suggest you guys use pipelines, scikit-learn pipeline. Very convenient, very convenient. Well, I said there are two ways of using pipelines. There are questions, but can I see new questions? Which ones are, what is F regression? F regression is calculating how related your independent variable to dependent variable. Okay, you can check from very basic statistics book. Okay, that's that much. What is the difference between feature selection? Feature selection is you are reducing number of features. You are selecting a subset of features. Feature extraction is you are creating new features from your already available features. Okay, for example, you have X1 and X2 as two features, and then you can add X1 times X2, and then X1 squared and X2 squared as new features. This is feature extraction. Why not scale the entire data set before we split the data set? I just answered this question, right? If you do this, that's gonna be a mistake. Scaling before you split will create problems. Do not do that, please. First split and then scale. Okay. All right, guys. So yeah, I said you can create pipelines in two ways. This is the first way we already saw. So when you do this, what scikit-learn does is, so inside your pipeline, you have standard scaler and you have k-nearest regressor. What scikit-learn does is, these are the steps of your pipeline. Step 1, step 2. Scikit-learn automatically will name them as standard scalar, all small letters. So this is your original name of the transformer, right? This is the original name of the transformer. Scikit-learn will use all small letters as the name of your transformer. Okay? And this is your estimator. Scikit-learn will use all small letters as the name of your estimator, because you might later on may refer to the steps inside your pipeline. Okay, that's the next thing. Maybe we can talk later. So you can do this way. Well, if you would like to have the flexibility of naming your own steps, then you can use capital pipeline, make_pipeline. They both are creating pipelines, but capital pipeline, what you do is you are creating a list of tuples. Each tuple corresponds to an estimator and its name. So standard scalar is the transformer, the first one, and this is the name that you give to this standard scalar. So here you are naming it yourself. Here, as you see, this is also a list of the tuples, but that is the steps of your pipe. The names are created automatically by scikit-learn. Here you are giving the names yourself. That's the only difference. Okay. You can use pipeline inside the grid search. Here I am creating the pipeline. Okay, same standard scalar. Here, this is my, you know, from last week's class, right? This is my grid search parameter. Number of neighbors is changing from 1 to 9. And inside the grid search, now instead of using k-neighbors regressor, I'm using k-num pipe. So what is happening here is, for each parameter value, let's say the number of neighbors is 1, my data set will be standard scaled first, and then will be fit. My k-neighbors regressor for the k-neighbors equals 1 will be fit on my trained data set. Okay, you can use pipeline inside your grid search. Okay, so let's, we don't have too much time left, but let's not finish this class without doing anything hands-on. So let's just do this example. I hope you have the file from last week and you have the data set. So let's see, where is the data set? So you can simply run this part here. Let's run this part. So I loaded the data set. Okay, train test data set. It's here, it's still loading. And as it is loading, let me check the. Feature selection of 5% removes, I mean, it removes 95% of the features that are, that their F regression, in this case, F score is less than that 5%. So what it does is it just sorts out all the features depending on the score that they get for that F regression score. Okay, I answered scaling data set once. Why not more? I think I answered that question. Some questions are coming all. Okay. Yeah, I think my data is loaded. All right, so let's continue. These are all last week's notes, right? Okay, now I'm gonna implement my k-neighbors regressor to fit both not scaled and scaled data sets. So, here my scaled data set. Let's also run this. This is from last week. I am using standard scalar, and I am fitting my trained data sets, fitting and transforming my trained data set. So now let's use k-neighbors classifier. So from scikit-learn neighbors import K-neighbors regressor. Okay, I'll be using regressor this time, not classifier. K-neighbors regressor. And let me instantiate my regressor. Okay, not just instantiate, but let me fit. Okay, on my first not scaled one. Okay, and then let me just print the score. Okay, this is the score. KNR is the object I already fit, and then I will be testing and getting the score on my test data set. Okay. Okay. Now, this is 0.46, not very great, right? So now let's do the same thing, but this time on my scale dataset. Where is my scale dataset? Here, right? X-train scaled. Okay, and then I need to create my scale test dataset. Again, what was my object, scalar object? Scalar. So I'll use that object, which is already trained on my trained dataset. Scalar dot transform. I'm not gonna be fitting, right, on my test dataset. X test. So this is my scaled test dataset. So I'll use the scaled one. I'm not scaling my target variable. And let me see. Not very great, but you see the difference, right? K-neighbors is very sensitive to scaling, very sensitive to scaling, okay? Okay, so let's do the same steps for random forest regressor. So this time I will be importing. Random forest is an ensemble model. Okay, imports random forest. Random forest regressor is an ensemble of decision trees. Remember, decision trees are not, they are immune to scaling. Okay, they don't care about scaling. Let's see. Okay, let's instantiate our random forest regressor. Okay, and number of estimators. This is number of trees that I will create for this. That's why it is forest. It's a forest of trees. Okay, and if you guys also use this random state equals 0, you get the same results with me. Okay. All right, and then let's fit this on our trained data sets. And later on, we'll do the same thing for our test data set, okay? And then let's just calculate the score on our test data set. All right, okay. Ref equals. All right, so this is the score of random forest. As I told you earlier, right? Random forest is a very good benchmark model, which you baseline or benchmark model, which you can use to start with working on your data set. It will give you really good results. And it's hard to beat random forest. It's an ensemble model. It's hard to beat ensemble models. Okay, then let's do the same thing, but this time on our test data set, as I said, I don't expect a big difference. Actually, I don't expect any difference at all. Let's call it RF2, and then let's fit RF2 on our test data set. I'm sorry, scale data set. And then let's score on our. Okay. There is no difference, right? So random forest decision trees are not affected by having different scales, okay? But as you see, k-neighbors regressor or k-neighbors classifier, support vector machines, neural networks. When you're working with images, you will see that you are doing scaling too. These guys are really affected by the scale of your data set, right? Okay, I wish I could cover more today, but I'd like to stop here and we'll continue next time. Okay, I'll finish this pre-processing next time, and I'll post because I didn't cover so much, but I'll still post an assignment, just some hands-on experience for you, so you can play around with the data set and scaling. Okay, guys, thank you very much for listening, and I'll talk to you next time.